Hey, everybody, this is Miss Wiesen, and you're getting ready to listen to the third podcast here in our Unit 6 Thermochemistry unit. And this lecture is basically an extension from the last podcast that you heard. Now, this is when we started talking about the concept of enthalpy, which, remember, in thermodynamics is the equivalent to the total heat content of a system. And remember what we defined the system as? The system is the thing we're studying. In other words, it's oftentimes the reaction at hand that we're investigating. Now, in today's podcast, we're going to learn about several other ways to look at enthalpy and to calculate enthalpy. But before we begin, I just want to quickly remind you that if you go to your AP reference sheet and you scroll down to the area that says thermochemistry and electrochemistry, you're going to see several given formulas. And you should start to recognize as we go throughout this unit some of these. And if you take a look at this first one here, the Q equals MC delta T, we learned that in the last podcast. We qualified that as calorimetry, being able to use this equation to calculate the heat content of a system. Well, today we're going to learn about calculating enthalpy, or the heat content of a system, using something called Hess's law. Now, it's important to note that Hess's law, it generally states, the definition is not on your page, but Hess's law states that regardless of the multiple stages or the multiple steps in a reaction, you guys kind of learned about the concept of a reaction mechanism in kinetics, that oftentimes complex reactions happen in a series of steps. Okay, well, it just so happens that regardless of these multiple steps or stages that a reaction occurs in, the total enthalpy change for that particular reaction is indeed going to be the sum of all changes. Now, we're going to look at a formula here, and you can already see it on the screen. I call it the Big Mama equation. Again, don't write that on your AP test. I just kind of give it funny names for you to remember that this is actually an important equation. We call this Hess's law. And again, I'm going to draw your attention to it down here. Now, you don't need to memorize this because it's on your AP reference sheet, but you certainly need to know how to use it. So when you use Hess's law, you're going to be given a series of enthalpy values for specific compounds. Now, these values have already been predetermined scientifically in the lab, and so you can actually go to the back of a textbook and look in the appendix or Google it online. And so oftentimes you're going to need to be given these enthalpy values, or you can see here that they'll be represented in a data table. Now, on your homework, if for whatever reason I did not give you any enthalpy values on your homework, I'm going to encourage that you use your textbook to look those up. And you got to go to the back of your textbook. That's where the thermochemistry appendices are, with enthalpies and entropies and things of that nature. And so today we're going to focus on delta H. I want you to recall that when you see this knot here, this NaUGHT, that is a symbol that represents a value, an enthalpy value, that was determined at standard conditions. Remember, standard conditions is not the same as STP, but similar. The difference is standard condition is occurring at 25 degrees Celsius at 1 atmosphere of pressure, and if solutions are involved, the solution would be 1 molar. Okay, so in other words, when you're given enthalpy values that have that knot symbol, those are values determined in the lab at standard condition. Okay, so just a couple of reminders before we hop into some examples. The values for the values that you see in these tables are defined as the value given for the production of 1 mole of that substance. A big thing that's going to really help you, if you are looking, when we go to do calculations, if you find elements by themselves in their pure form, or even diatomics, they're always going to have a 0 enthalpy value. Okay, that's important to know when you're doing your calculations, and you'll see here in just a second what I mean. Okay, let's take a look at Hess's law, the equation. If you see here, it's literally defined as the change in enthalpy at standard conditions for any reaction is equal to the sum of enthalpies of the products minus the sum of enthalpies of the reactants. Don't forget, when you see these symbols, it means sum of Exercise 8 is a good place to start. You can see that you were given several substances and the enthalpy values at standard condition. I'm going to give you a heads up. You can see here, if you're doing any kind of multiple choice question, and since you can't use a calculator on the multiple choice in the AP test, if you see values that are like decimals, it's okay. It's appropriate to round those numbers for multiple choice questions to make the calculations easier for you. So just so you know. Given the information above, it wants us to calculate the overall change in enthalpy for the reaction. Okay, and so here is our reaction, and I'm going to use Hess's law. And so really quick, I'm just going to rewrite that here as a reminder. Okay, there you are. So we're going to use the Big Mama equation. We're going to use Hess's law. Now, I'm remembering from what I said above. I'm going to go back up here, and I'm going to highlight it in a different color. Elements or diatomics are going to have an enthalpy value of 0. Can you go ahead and tell me in this reaction right now, where are our diatomics or our elements? There's only one. It's right here. It's the aluminum. It's elemental. It's by itself. And so I know that the delta H of this is going to be a 0. And so I'm going to go ahead and just carry my equal sign down. This is how I do it, you guys. First off, you need a balanced chemical equation. Clearly, they gave that to us already. And if I'm looking over here, I'm going to just kind of highlight this for my eyeballs. Here's all my products. All right. And then I'm going to highlight in pink my reactants. So anyway, when I'm doing this problem, the color coding helps me separate things out. And so follow my logic. If we're gonna subtract, we're gonna take products and subtract from reactants. And so don't you agree that we are then going to take the sum of the products? So this is visually the way to represent that. Notice how I'm pulling down the coefficients here. Okay, and we're going to subtract that. So by the way, this subtraction sign is this subtraction sign right there. I'm going to come over here, and now I'm going to take the sum of the reactants, but there's only this one reactant over here, this ammonia chlorate. Okay, let's plug in values. Okay, make sure you include the signage. So negative 1676. All right, I'm going to go to the value for aluminum chloride. I'm looking up here. There it is. It's negative 704 kilojoules per mole. I'm going to the nitrogen monoxide. Be sure you carry down that coefficient. And it's right here. It's 90 kilojoules per mole, and it's positive value. All right, and then I got 6 waters. And I see water is negative 242 kilojoules per mole. Okay, that is, let me go ahead and close brackets. Let's go ahead and subtract that from our reactants. And I've got 3 ammonia chlorates. And I noticed that the table tells me it's negative 295 kilojoules per mole. Okay, all right, follow the order of operations and just do this basic math. Okay, I'm going to give you a second. Put me on pause and see if you actually can arrive at the answer that's indicated there at the bottom of exercise 8. Negative 2,677 kilojoules per mole. This is, according to the signage of the enthalpy value here, negative indicates that this would be an exothermic reaction. Heat energy from the system is leaving and going to the surroundings. All right, that's one example of Hess's law. Let's do exercise 9. Is, again, gives us a reaction. I'm going to, I quickly look here, and this definitely looks like a combustion reaction. How do I know? Because I have some hydrocarbon in the presence of pure oxygen, and then I see that carbon dioxide and water are produced. Now, you should notice here that we have an enthalpy value added to the products of this reaction. If this value is written as a part of the products, remember, this means that that was the energy that was produced in this reaction. So when you produce the energy, when it's a product, it's exothermic. So energy is being released from that system and going into the surroundings. So really, we know that the delta H is negative 2,800 kilojoules. Okay. Now, having that in mind, we also learned that we have to remember elements and diatomics are going to have an enthalpy value of 0. And so right now I see diatomic oxygen and automatically know that that's not going to be a part of the Hess's law equation because, well, the value is 0. I am going to let you know this is a really important point. The equation you're obviously going to use if you read this problem, but if you go to the very last sentence, it's basically we're calculating the delta H of the reactant, C6H12O6, glucose. And you can see that's a reactant here. We are therefore going to be solving for the delta H of reactants. And of course, it would be at standard condition because I noticed the values given to me here in this table are at standard condition. So I'm going to be using the Hess's law. Don't forget the delta H of reaction. I'm just rewriting it here. And here's why I rewrite these equations over and over again. Because you get points on the AP test for doing it. You don't get all the points, but you can easily get 1 point for a problem just by writing the equation that would be appropriate to use in that circumstance. So if I were you, I would get used to rewriting or indicating when you're working a problem what the equation is that you'd be using, because you'll get points for it. Now, in this problem, we again learned that we're going to be solving for the delta H of a reactant. So now what I'm going to do is just plug in values, and I'm going to let you guys know that I'm going to keep my Hess's law equation in this form when I go to do this practice problem. And then when I get all my values, I'll then rearrange the equation to solve for the heat of reactant. So again, set it up. You're going to want to, left of the equal sign is the delta H of the entire reaction. Gave it to us in the problem. It was negative 2,800 kilojoules per mole. So the products, go over here to the products up above, and you've got 2 of them. You've got CO2 and water, of course. Don't forget to carry down that coefficient. And remember, when you're taking the sum of the products, this is what you're really doing, okay? And you're going to subtract that from the enthalpies of the reactants. But now I'm going to go ahead and just plug in values. Notice I'm not including units over here on the right. It just starts to take up too much space for me, but you should definitely be in the habit of always writing your units. Oops, and this is 0.5. All right, I'm going to go ahead and just continue on calculating. Don't forget to distribute those coefficients to the appropriate numbers. So what do I get now? I'm going to go ahead and simplify everything inside the brackets here and then bring them over to the left side of the equation so I can get the enthalpy of reactants all by itself. So we want to get rid of this negative sign in front of the what we're solving for. So you just multiply both sides of the equations, both side of the equation here by a -1, and at which point you would get your final answer. The delta H for glucose, which is the only reactant in the equation, is negative 1,275.8. You can see I rounded it here to 4 sig figs. Don't forget my units. And that is the enthalpy formation for glucose. All right, we'll do exercise 10 in class. I make the note here so I don't forget. Please remind me if I do. Now, we learned previously that reactions can happen in a series of steps. And so if you are actually given the combination of chemical reactions, remember that the combination of these reactions must add up or equal the overall reaction we're trying to achieve. And here's the thing. In some cases, as you can see in exercise 11, not only are you given the overall reaction, I highlighted it in yellow, you're given the series of steps that it's happening in. But also, what else do you notice here? In this particular case, you are given the enthalpy of reactions for each step. And so one of the different ways that you can apply Hess's law here is if you are given a series of equations with given enthalpy values, you can actually rearrange these equations in such a way that the overall enthalpy of that reaction. Okay, so let me show you what I'm talking about here. There's a couple of tips that you need to know. If you have to reverse an equation, you're going to need to reverse the sign of the reaction. Again, you're going to see an example in just a second. Another really important tip here is if you have to take any equation and multiply it by a certain factor to get coefficients and substances to cancel, you're going to also need to multiply the given enthalpy of that reaction by the same factor. And then obviously you need to make sure that you follow up and double check that you arrived at the exact, at the overall equation. In exercise 11, we are asked to calculate the enthalpy for the overall reaction. You can see it's listed there. And we see the reaction mechanism, the steps that it takes to get there. And so remember, we call those elementary steps. Okay, so one of the places that I start here is I look at the overall equation and I see what is on my reactants and side, and I see the substances on my product sides. And then I go to the elementary steps to make sure that those substances are in the correct places. For example, if you look at this reactant H3BO3, I notice that in the first elementary step, it is written as a reactant here. So in elementary step 1, I would not reverse the equation because it appears the substances are on the correct side. If you look at elementary step 2, you can see some substances here, H2B407, and you can see water. Those are listed as reactants here. But if you go back to the reaction, I see water as a product. That's pretty much an indication that you're going to need to flip that reaction. And so what do I mean by that? Flip the sign. So it'll be positive 11.3 kilojoules per mole. And instead of writing it like that, you would consequently do 4 HbO2 and bring the reactants over to the products now. H2B407 and H2O. Now, I noticed that when I do that, oh, by the way, check elementary step number 3. Do the substances in the reaction and the overall reaction tend to align with the substances you're seeing in elementary step 3? Well, look at my reactant here. I don't see that in the overall reaction, so that's probably going to be an intermediate. But for now, let's go to the right side of this elementary step, the product side. B2O3, oh, I see it as a product over here on the overall reaction. Oh, and I see water too. So I'm clearly not going to flip reaction, elementary step reaction 3. That I need to start cross-canceling some things. And I notice that if I go back to elementary step 2, I have 4 HbO2. But then I come up to reaction 1 and I only have 1 HbO2. Okay, they're on either sides of the arrow, so they're going to cross cancel, but I have more in elementary step 2, I have 4 of them, compared to the 1 in elementary step 1. Now, here's the thing. Do you see HbO2 over here in the overall reaction at all? No. It's going to be an intermediate. It's going to have to fully cancel out because it is not a part of the overall reaction. So I've got 4 in my elementary step 2, but only 1 in my elementary step 1. What I need to then do is multiply elementary step 1 by 4, a coefficient or a factor of 4. And when I do that, I need to distribute that 4 to the entire equation. Don't forget, if you take a coefficient and multiply every step by that coefficient, you also need to do the same thing to the enthalpy for that particular step. Becomes a negative 0.08 kilojoules per mole. So I think right now we can, down below, I'm going to rewrite some of this. All right, so let's cancel stuff out. I'll use my red color. And the 4 HbO2s cancel. I notice that in the next reaction, this product cancels with that reactant. I'm looking and I don't see anything else. Go to the left side, left of the arrow only. Carry down anything that remains. 4H3BO3. Okay, draw my arrow. I've got 2B2BR2O3 and 6 of these water molecules. Okay, I notice that it looks very similar to the reaction that was given to me. But take a look at your coefficients, 4, 2, and 6. You need to reduce those. Okay, so 2 goes into 4 2, 2 goes into 2 once, and 2 goes into 6 3 times. There we go. That looks a lot like the overall reaction. And so what you have right now after you reduce the coefficients is indeed an overall reaction that matches with what was given to us. And so when you add up the enthalpies now, negative 0.08 kilojoules per mole, plus 11, positive 11.3 kilojoules per mole, and positive 17.5 kilojoules per mole. If you sum these all up, you should indeed arrive at 14.4 kilojoules per mole. So that's one way to do it. All right, last way is using something called bond energies. This is very similar to Hess's law, but here's the big concept here. When you are breaking bonds, you are adding heat. Those bonds are absorbing the heat energy. If you are forming bonds, creating two elements coming together, if you will, that is going to release energy. It's going to be exothermic. For many of you, it might sound opposite of what intuitively you would think. So it's important to know this when you're using this method. So one of the things that I think is helpful when you're given a problem like this is to write the reaction out via Lewis dot structure. Because what it allows you to do is it allows you to see the bonds that are forming between the individual elements. And that could be a single bond, a double bond, or a triple bond. And you could probably rest assured that the bond energies associated with double and triple bonds would be much higher than single bonds. So remember in the equation just up above here, bond energy is broken. So broken minus formed. All right, so you would really literally just follow that format. So if these are being broken and these are being formed. So let's go ahead and just do the value. Let's calculate 432 kilojoules per mole plus, I'm just carrying that plus sign down, 154 kilojoules per mole yields 2. And 2 because that's our coefficient. We have 2 HFs. And each one is 565 kilojoules per mole. Now, when I do my calculations on this, I see that I get 586 kilojoules per mole on my reactant side. I can go ahead and replace that arrow minus. Okay, and so what I get here on my left side, I get a total of 586 kilojoules per mole. And on my product side, 2 times 556 is 1130 kilojoules per mole. And let's go ahead and bring all of this to one side. Let's bring this over here. So you would subtract 1130. And when you do that, big arrow, you guys, I'm finishing it over here to the right, I get negative 544 kilojoules per mole. So this indeed is an exothermic reaction. So that's how you would use bond energies. Very similar to Hess's law, but you're coming from the perspective of bonds being broken, subtracted from bonds being formed. Again, there's just a couple tidbits right here at the bottom of page 11 that you need to know. And I'm going to go ahead and call it quits for now on enthalpy. In our next podcast, we are going to talk about the second law of thermodynamics. I appreciate you so much for listening. Thank you so much.